I really don't like starting on anything without a clear picture of the end. I also hate planning. It's a weird dichotomy that leaves a lot of ideas floating around in my head that never see the light of day. But there's one idea in particular that just keeps kicking its way through the chaos, and it's been river dancing up there for a couple years now. So against my better judgment, and without a proper plan, I'm just gonna start. Welcome back to Inheritance Machining. So this is kind of a big project, one that I already know is going to take more than one video to build, and I actually thought about not really saying what it is until the final segment, but I feel like that would be the biggest blue balling in machining YouTube history. So here it is. I'm making a radius turning tool for the lathe. So I can make stuff with radii on the lathe. Off the top of my head, there are a few ways to do this. With a ball turner like this, with a form tool like this, or just freehanding it like this, but I don't really like any of these. Ball turners are really only good for making balls, and some radii in certain conditions. Form tools are only good for one size, and you have to keep all the sizes handy. And freehanding it, I think it's fair to say that none of these approaches are satisfactory. And don't you even think about mentioning the cursed 3-letter acronym. My idea is way cooler anyway. So imagine this. Basically a set of wheels with a connecting arm, like an old steam train. Now attach a lathe tool to that arm and you can see that it traces the path of a circle. The path of a circle that can be used, for instance, on a lathe to turn a radius. But what if I want a different radius? Well, I can just change the offset of that connecting arm like this. Now it makes a smaller circle. And yeah, that's the gist of it. But isn't it cool? I can't say I've ever seen a tool like this for a lathe, ever. Though that may be for a good reason because there's literally so much more I have to figure out to make this all work. Like I said, it's been bouncing around in my head for a few years at this point, and I could never get it all straight. Then it occurred to me to just start modeling something. I know the basics I'll need, like 2 train wheel things, and some sort of base plate with bushings so they can spin. Above that, I'll need another set of axles in this block that will make up the connecting arm and also serve as a tool holder, leaving the problem of how to adjust the offsets to create the different radii. And I found inspiration for this not so far away. Boring heads. They ride on a pair of dovetails, are adjusted with a screw, and are locked in place through this clamping slit thing. So that's basically exactly what I'm going to do here. In all fairness, I kind of already knew this is where this was going when it was all still in my head, but it's just nice to be able to quickly iterate on design details like this in Onshape, which is something I've really come to appreciate about this software because it doesn't get in the way and it just works. And it just got even easier with their AI advisor that can take my stupid questions, decipher what I meant, and provide actual useful instructions on how to do what I want. Get the same professional version I use free for 6 months at onshape.pro/inheritance machining. After a tiny bit more fine-tuning, I've got the design to this point. Not finished by a long shot, but good enough to get going. And honestly, if I just start making some of these parts, I can put an end to my indecision fatigue. That, and I'm tired of planing. I've been working on this long enough that some of my materials have already arrived, like this nice girthy shaft of 1144 steel, otherwise known as stress-proof. I'll explain why I chose this in a minute, but I can assure you it's not for getting a nice pump going, so let's cut it down to a more manageable size. The only pieces I have fully designed at this point are the spindles, so let's start with the tops and work our way down. The major diameter on these parts is near what the bar is to begin with, but the rest gets a pretty dramatic weight reduction. This would be a problem for most steels because they'll have a lot of residual internal stresses from how they're made, which would cause some pretty significant bananification, but not with stress-proof. Stress-proof is stress-relieved. So after all that material removal, this thing is still damn near perfectly straight. The second reason for picking this magical alloy is because it lets me be lazy. I designed the spindle to ride on bushings, and the direct contact is going to be prone to wear. The ideal solution would be to use a hardenable tool steel, heat treat it after machining, then grind it to size. In other words, a ton of work for something as complex as this part will be. But stress-proof comes already fairly hard at Rockwell's C25, so it strikes that perfect balance of machinability and durability. At least that's what I've convinced myself of. After all that rambling, I have this. So I just did it all again, only this time with a boo-boo. What? I don't always make the best decisions. In fact, I have another questionable decision I need to make. It's been a while since I've given my wife a new man to look at, so let's surprise her with a nice Henson shaving sponsorship. Other than giving my wife a good scare, I also like working with Henson because they're a company after my own heart. Not because I'm much of a shaver, but because Henson are machinists, and I like machinists. Machinists are good people. They strive for perfection in all aspects of their craft, and at Henson, they put the quality of their AL13 razor above all else. Made with sustainable materials completely in-house, they've developed their own CNC machining approaches to achieve the precision that sets their razors above the rest. Because you may not realize it, but to get a close shave, you need close tolerances. And with a razor-sharp blade literally gliding across your skin, if you get this wrong, it's not going to be a good time for anyone. So the extra pride Henson takes in their razor means you can take pride in your morning routine. Not bad for something that will pay for itself in 6 months compared to all the other approaches. So support a machinist and get 100 free blade refills when you use the code inheritance at hensonshaving.com/inheritance or click on the link in my description. Now, let's see what Paige thinks of this machinist's handiwork.
Also,
What are those?
those are my blue balls. I'm ready for my roasting.
You ready?
Yeah. That's a good face.
I don't hate this one.
No?
No. It seems extremely complicated.
It took a while to figure out. It's called the Balbo. Robert Downey Jr. kind of wears.
Yeah,
something like
yeah.
This. His kind of comes down and goes whoof whoof. I only know this because I was looking up beard styles, not because I'm extremely familiar with Robert Downey Jr.'s facial hair. But you like it.
I wouldn't go that far. I'm having very mixed feelings about this one.
I might need a haircut. There's too much gray going on.
That might help. It's well done. I'll give you that. Yes.
It's uneven.
It is uneven. I was not going to say anything.
You're only like 10 hairs tall, so if you go one too far, it's just, you're done. And then if you go uneven, then you got to take more off the other side, and then you end up just whittling away until you get a little pencil.
Girls have this problem too, but when we're doing our liquid eyeliner.
You just keep adding and
yes,
adding and adding. Then
until you
have
look
big,
like a panda.
thick-
You don't look like you.
Yeah. I haven't looked at myself enough. I look thin. Well, that might just be the mirror. Oh, yeah.
I think confusion is the primary emotion that I'm feeling. It's not like or dislike. No, you know who you look like?
Oh, no. Here it comes.
Puss in Boots. It's Puss in Boots, Antonio Banderas, Zorro facial hair.
So hot. Mm-mm. Yeah. Mm-mm. Yeah. Thank you. Maybe.
What do you say we get back to something more in my wheelhouse? The rest of this part is a job for the mill, and to keep all the square bits square, I'll use the square collet block. First is the hole for the offsetting screw. Remember this guy from the boring head? I have to do this hole first while I still have the thickness to my advantage. Ever try drilling a hole partially over the edge? Take my word for it and don't. At the bottom of this bigger hole is still the smaller one for the tap, but unfortunately it doesn't have the reach to get the job done. No shame in admitting when you need a little help though. Now to turn this hole into a proper bore. I want this to be a nice fit for the screw I'll make later, so I'll sneak up on the diameter little by little and let the machine do all the work. "90 degrees to that is a triplet of countersunk clamping screw holes, 2 of which end up off-center, which isn't exactly the best way to start a hole. But by going at it gently with a rigid spot drill, I can make sure it doesn't drift off position, and I can just bring my smaller drills in here like normal. The real reason I did this though is that the end mill I needed to counterbore these is not center cutting, meaning I need to have the material in the center removed before I could even use it. Otherwise I would have just started with this. The top little bit of the holes gets drilled larger for screw clearance, then what's left gets tapped clear through to the bore. After bringing the shaft to attention, we can finish it off. After shaving a bit off the top to bring this to thickness, I'll check the dimension in all 4 directions to make sure it's staying square. I want the dovetail to be perfectly on center with the axis of the shaft, so I'll use the coaxial indicator and some fine adjustments on the hand wheels until that needle stops dancing about. Then lock it in and begin milling the pocket for the dovetail. The majority of which I'll do with a straight roughing end mill, leaving a little left for the dovetail mill to do its thing. Dovetails are a bit of a weird thing to measure because you have to do so sort of indirectly. First, you have to make sure the depth is where you want it. Then you have to drop something precise and round against the angled faces that you can actually measure. Of course, making sure that not only the distance between them is correct, but also that the distances from each side are the same so that it's centered. And the numbers, they just come from the model. After a little bit of chamfering on the sharp corners, that leaves just the clamping slit, which is a simple matter of leaning this whole thing over, running the slitting saw just under the dovetail face, and crossing my fingers I don't accidentally cut this thing in two. Easy as that, the first spindle was done, and the second was the same, except no adjustment screw stuff. And another boo-boo. But now, with the upper spindles complete, we can move on to the lowers, which for the most part look a whole lot like the uppers, so let's just enjoy some therapeutic lathe work. Something I didn't mention is that the bushings I ordered for these shafts have slightly oversized bores. They also haven't been delivered yet, meaning there's no way for me to really fine-tune the diameters the way I would want to, so I'm leaving these oversized so that I can do that later. More specifically oversized to match the next largest 5C collet in my rack. This way I can guarantee a precise, square, and rigid clamping in the collet block, which doesn't happen if the part is smaller or larger than the collet's true size. I actually did this on the upper spindles as well, but I was rambling on about metallurgy and facial hair. This time around, I'm going to start with the dovetail, getting the thickness where I need it, finding the center, and again roughing away most of the metal. Now there's a subtle difference in this round of dovetails other than them being male instead of female. There's no way I could get all 5 facets of the dovetail interfaces perfectly matched on both halves. I mean, I can get them pretty close, but I think it will be better if I'm a little selective on which ones to target. In my case, the middle top and the 2 angled faces seem like the smart choice. This will give me the most rigidity when the offset is at its extreme reaches. So I'm leaving about a thou of clearance on the remaining 2 faces. And the fit comes out absolutely perfect. Not the least bit wiggly and just a bit of friction. and the clamping screws take almost no torque at all to lock this thing down. I'm kind of downplaying this a bit, but the fit is unbelievably satisfying. Now all I have left are the scallops for the adjustment screw. Something I didn't really feel like fussing around with, so I just bought the cutter I needed. Lastly are a set of shallow cuts on the backside at 3, 6, 9, and 12 o'clock. In theory, I can use these for detents to square things up on the final tool. I say in theory because I haven't quite figured that part out yet, but now I know what direction I have to go. And that's the lower spindle complete. Again, the second was the same, only no screw scallops, and 1, 2, no extra band-aids this time. Now I have a nice pair of spindle pairs ready for their adjustment screw, so let's whip that up next. This screw is a lot smaller than the previous part, so no sense in shortening our girthy shaft any more than we need to. This smaller piece of A2 will be fine. Actually, I prefer it for a part like this, for reasons I'll explain later, of course. But to start, we need to turn this shank down so we can thread it. And this is where the week I spent re-leveling this lathe in my last video really pays off. If you know, you know. Of course, I'm not overflowing with good decisions. When I tap the hole this screw is meant for, I just picked the finest pitch thread I had on hand, a 1/4-28. Which I only now realize requires swapping to a whole different set of change gears, which I only now realize after mounting the collet chuck and its change gear change hindering locking mechanism. Okay, now we can dicom the shaft, which I do for no other reason than it looks cool while threading, and sneak my way in little by little, pass by pass, until I have a nice fit with its future dance partner. This is a love triangle though, so I still need to match the scallops on the other dovetail half. And short of a proper grooving bit, I'll just use the parting blade. A bit of a faux pas, but it gets the job done. And I can part this off to finish out the other end. Despite the inconvenient design choices I've made so far, I would like for this tool to be convenient to use, and in my eyes that means it uses minimal tooling. I want the hex drive in this end of the screw to match what I use for the dovetail screws. Only trouble is, I didn't make a rotary broach that size. I have one close, but close is no guitar, so let's make one. But first, I gotta remember how to do this. Okay, let's go. This blank is a special kind of high-speed steel called silver steel, and it hasn't been hardened yet, so that means we can just make it on the mill. The pallet fixture makes it easy to set everything up for a 2.5 degree clearance angle I'll need. Then with a series of locating pins and clamps, I can use the hex collet block to work my way through the 6 sides, guaranteeing the resulting hexagon is dead center. I also need a set screw flat on the other end. Then with that all cleaned up and deburred, we harden. This will most likely snap, it's so brittle though, so half an hour in the tempering oven at 150°C and we're ready to use this thing. If you've never seen a rotary broach in action before, you'll probably miss the subtle nature in which it works. It probably just looks like I'm pressing this into the hole I just drilled, which I guess I am, but in reality the broach's rotation axis is 1 degree off from the lathes, so a combination of the angle, rotation, and pressure lets the broach slowly work its way into the bottom of the hole, making a hexagon. I'm a little worried this hex drive will get all fuggered up over time though, so I do want to harden it, at least just this end. And that's why I picked A2 for this. It's an air hardening tool steel, so once I get it red hot, just letting it cool down in open air will do the trick. And because there's no rapid quenching, there shouldn't be any distortions. Just a nice hard result. But I still want to temper it, partly because it's the right thing to do and largely because I can make it look cool. If I get the tempering temperature just right, at around 550 degrees F, it turns frickin' blue, which I think is pretty effing cool. So now when I put this in the spindle, not only does it look badass, but damn, it looks good. I was going to say it feels badass too, but I can't get past the aesthetics. The only downside, and I mean only, is that the 28 TPI pitch I chose for the thread doesn't lend itself to adjustment tick marks like my other boring heads, so no tick marks. But who cares when it looks this good? Now you may be wondering at this point, or maybe you've been wondering all along, I don't know, but you may be wondering why I only made one of these adjustable. The simple answer is, only one of them needs to be adjustable. In a roundabout way, this one screw will adjust both spindles, but that will make sense once this is all together. Which is going to have to wait until next time because there are several details I need to figure out before this will all work. Namely how to synchronize the two spindles, and how to hold them in the lathe. So let me know what ideas you have in the comments. At the very least, they'll bolster my own ideas. As always, thanks for watching, and see you next time.